Welcome back to Impact. And now we're on to our science topic. And Barbara will be interviewing Dr. Jim Napolitano, Professor of Physics at RPI. And Heidi, what's he going to talk about?
Well, that's right, Nick. He's going to be talking about the new discoveries with neutrinos and dark matter.
What are those? I guess we'll have to watch to find out, won't we?
Yeah, we will.
Okay.
Join us.
Thank you. Welcome. We're here at the science segment of Impact. It's our maiden voyage, and I am pleased to have my guest here today, Jim Napolitano, PhD from RPI, Rensselaer Polytechnic Institute in Troy, New York. Welcome. Good to see you, Jim.
Good to see you too, Barb. It's a pleasure to be here. I'm looking forward to this.
I'm so excited that you're my first guest and that we can talk about little things today. But let's start first off with an embarrassingly amazing CV resume. You're local.
Yeah, I grew up on Long Island, and I came to RPI in 1973 to go to college.
Oh, we don't have to disclose our age here on this show. And then you went further on for a master's degree at RPI?
Yeah, I finished after a little more than 4 years at RPI with a bachelor's and master's degree, and decided at that point that I really needed to go other parts of the country. So
you said sunny California.
California is where I ended up moving and spent about 5 years there. And after getting my PhD, moved to Illinois, worked for Argonne National Laboratory, and then a laboratory in Virginia, and I came back here in 1992.
And then the Northeast said, come back, come back. And so 92, so almost 20 years now at Rensselaer.
I'm in my 20th year at RPI in the physics department.
Right, in the physics department. So congratulations and welcome, and I certainly appreciate you being here. Before we talk about small stuff, particle physics, I wanted to talk about some of the big stuff, those balls in the sky that we see. So could we talk about like the solar system's composition and how the sun came to be and what we know about the sun and its previous history?
Sure. Well, this is something that's not my research field, but in fact I've had some opportunity to learn about it. I've taught astronomy and seen these things, and I've also picked up some things from the Center for the Origins of Life, which is
at RPI.
Which is led at RPI. We've talked about these things. So I have colleagues who do this. So the solar system, the sun, is about 4.5 billion years old, which is may sound like a long time, but in fact it's only about 1/3 of the length that the universe has existed, going back to the Big Bang. So the sun and the solar system are made out of recycled material. As our galaxy evolved over the past 13 billion years or so, there were stars were formed, and then they became exploded out, and that material got mixed up with the rest of the galaxy, and then all of a sudden another clump came by, and after a recycle or two, we ended up with our solar system.
Wow, so we're kind of like the ultimate recycle project?
In a large sense, that's really true. One of the things that's very fascinating is that if you look at the abundances of elements that come in from meteorites so that we know what the solar system is sort of made of, you can see specific signatures of elements that were created in one type of star that we call a red giant. You can see evidence of other types of stars that were likely ended up in supernova. These things all mixed up and created the little bits and pieces that created our solar system.
So I've read that all of the elements on the periodic table up to iron we can explain through a first-generation star, but our star, even though it's kind of normal and kind of plain to us, is really spectacular because we have a larger abundance of elements in that star.
A lot of that is, I guess I'd say, basically correct. Iron is a special element because it is the most stable nucleus. It's it costs you more energy to pull all the pieces out of an iron nucleus than it does just about anything else. We do know that in so-called first-generation stars, it is possible to make some very heavy elements by sort of neutrons capturing on other things in the atmospheres of red giant stars, and this is one of the signatures that we have to know that we were recycled from one of those stars. But one of the things very clear, the very first time a star is made, the universe, when it was born, was almost entirely just hydrogen and helium. And if you look at a star that was born out of that mixture, about 25% helium, the rest hydrogen, it ends up making, with a star like our sun, it makes some carbon and a few other things, but it pretty much stops there. So we know that to get even into iron, you need more than just a first-generation star. You need some other mixing, some particularly heavy stuff that's able to burn things.
So
and that could happen.
We see on this planet, we see uranium, which is a really heavy one, barium, I'm trying to think of some other, neon or argon, those would be pretty heavy.
Light. Well, those are relatively light.
Ultimately light, but that shows us that we're the product of other supernovae?
The thing that's most striking to show us that we're products of supernovae are by looking at a very special class of extremely heavy nuclei. If you look at the way nuclei are put together, and this is really some basic nuclear physics, what you discover is that for certain numbers of protons and neutrons, if you put them together, you get a particularly stable nucleus. Nuclear physicists call this islands of stability.
Islands of stability, a new ride at Disney.
That wouldn't be a bad idea.
Yeah.
Some of the more common examples are tin, lead, I think barium maybe one I'd have to think a little bit. So there are some elements where signatures are that's the case. And if you see those elements very clearly, that tells you that they were created slowly, and we see some processes in stars where that could happen. We see some very interesting evidence, though, of abundances of elements that are close to these magic numbers, but a little bit further away. It's very distinct separate signatures. Those had to be formed in such a way so that the neutrons that are added to these islands of stability,
in that nucleus,
that nucleus, that had to happen so quickly that before the nucleus, which would have been radioactive, decayed away, it captured a neutron and turned it into something else. Ooh. So very rapidly they climb up the ladder, and that can only happen in environments that are extremely intense with very high neutrons. And our best guess is that that happened in supernovae, although I know from some people, Professor Becky Sermon, for example, at Union, could explain how we just don't really know exactly how that happened. So there's some mysteries. Our best guess are supernovae, but there are a lot of problems that need to be solved to understand where we came from.
Particle physics and physics in general is always a dynamic field. Certainly you're excited about it. I'm certainly excited about it as well. Just recently, the Nobel Prize for Physics was given to 3 researchers here in the U.S. Could you explain why they were awarded the Australian. Why they were awarded the Nobel Prize?
Sure. It's an interesting case because the history is fascinating. When Einstein first wrote down his theory of gravity, one of the things he insisted on or put into his theory was a number called the cosmological constant. And he had to stick this number into his equations because if he didn't, it would indicate that the universe had to be constantly expanding. And back in 1920 or thereabouts, everyone knew that the universe is static. Look, everything changes, it's the same. Some years later, Edwin Hubble did some measurements and was able to discern that things that we now call galaxies are much farther away from us than the stars that we see at night. And in fact, the further away these galaxies are, the faster they seem to be receding from us.
So they're moving away.
Basically means that all of space is expanding. If you think about it, if you have a bunch of different things and everything is moving away from everything else, if you're standing on any one of those points, the way we are in our galaxy, you would see everything expand away, and the further away it is, the faster it would look like it would be receding. So this so-called Hubble expansion of the universe has been known for, pretty much well established for 60, 70 years or so. It's curious that a Nobel Prize, I believe, was never given for any of these discoveries, although they were fascinating.
He got a telescope out of the deal instead, I guess.
Yeah, we used the Mount Wilson telescope. He was an interesting guy. He was a lawyer, actually, self-taught scientist. Interesting situation. But anyway, so we knew the universe expanded, and for many years, while I was growing up, while I was teaching the subject, one of the things that people tried to understand was the so-called Hubble constant. It told you the rate at which the universe was expanding. It's a really interesting number because if you just take the inverse of that number, it tells you when the universe was all in one place, and that gave you the age of the universe. And people debated.
So we could find out when the Big Bang happened by just turning Hubble's constant over.
Literally, that's how you do it. In fact, when I said the universe was 13 billion years old, that's where that number comes from. It's from a measurement of Hubble's constant. People always wondered various things, though, about the universe. One of the things people always wanted to measure was how fast the universe was decelerating. If you think about it, it's like something expanding away from itself and the gravitational forces are getting weaker and weaker, but they're still taking energy out. So even though something might explode, then it'll slow down and go slower somewhat later. people always wanted to look as far out as you could in the universe to try and measure this deceleration. That would tell you some details about how the matter was distributed. People at Berkeley and I guess in Australia tried to do this by using far distant supernovae to look very, very far out in the far reaches of the universe to try and measure this deceleration and compare it. And they discovered something fascinating. At very far distances, the universe is not decelerating, it's accelerating. The universe is getting faster.
Opposite of what we thought.
Absolute opposite of what you expected. And that's what the Nobel Prize was given for. Ironically, what it means is that that cosmological constant that Einstein put into his equations that he called his greatest blunder, supposedly, that constant has to be there with, in fact, the opposite sign.
Ooh.
It means that as you get further out, there's some energy that we don't understand, it's called dark energy, that's causing the universe to expand more rapidly. And this probably constitutes the, well, different people have different points of view, but I would say it constitutes probably the biggest scientific mystery we have these days.
Well, so Einstein dropped a sign. So there's hope for students out there.
He didn't drop the sign. There's a lot of stories about his math. There's a great book I would recommend that it's actually sitting on my nightstand now that I've been reading about history of Einstein, how he made mistakes.
What book is that?
It's called Einstein's Mistakes by Hans Ohanian, University of Vermont. I recommend it. But anyway, you can read this and you can find out how a lot of these decisions were made. Physics, science is always I don't know if I'd say a competition or a tug of war, but a collaboration between theoretical physicists like Einstein, who tried to understand how the universe was built by using basic principles, and experimental physicists like myself, who make measurements and try and compare what you observe to what's predicted.
And when there are paradoxes between the observations and the basic science that exists, that's when growth in science happens.
Absolutely. I tell my students all the time that physics is a science where you start from assumptions and you work and make predictions from those assumptions. You compare experiment to those predictions, and if they agree, great, you move forward. If they disagree, and you didn't make a mistake in the experiment or a mistake in the equations, then you have to go back and look at your fundamental assumptions and readdress those. And that is how physics has progressed since the days of Newton.
So let's talk about this dark energy. The fact that the universe is expanding and it's accelerating as it expands.
That's right.
Means that it's not just about the stuff we see, the stuff we can detect with a telescope, whether it be a visible telescope or a radio telescope or an X-ray telescope.
Or X-rays or gamma rays, that's right.
So there's this other entity that now is deemed dark energy.
Yeah, well, realize what's going on here. We've got a large gravitating mass that was the universe, and as it expanded, gravity would have caused it to slow down. If it's actually expanding, it means that as you get large enough, there's something inside that's causing things to repel.
So more gravity somewhere else?
Well, it's a gravity that goes in the wrong direction. Gravity would cause things to attract, to slow down, not repel. So as opposed to this thing called dark matter, which we see because we look at gravity in relatively local environments like galaxies or in galactic clusters and things like that, where we see a lot more mass that can be accounted for by just the light, the luminous stuff that we see.
Let's take a step back for a second. Gravity and mass are related.
That's right. Gravity, this is one of the things that was sort of a mystery to Newton. He figured out that this looked like it had to be the case, that mass, this thing that resists a force, is also the quantity that causes gravitational attraction. And to him, it was a great revelation that there was that was the way that you can make things attract and work. Great supposition. Einstein put these two concepts together. So now, yes, mass, gravity, these are the two things that are combined.
So we've got dark mass, dark matter. We have dark energy.
Right.
Don't know what that is.
Don't know what that is. We don't know what dark matter is either. But
Are dark matter and neutrinos related somehow? Because there's been a lot of neutrino news lately.
That's right. Dark matter and neutrinos are related, but we do know that dark matter cannot be neutrinos. We know enough about neutrino physics to know that even there are a lot of neutrinos out there, they can't provide the additional gravitational attraction that we see in galactic motion and things like that.
Well, we've run out of time. It went so fast, and we haven't even gotten to neutrinos yet. Jim, you'll have to come back some other time.
I would be more than happy to come back and talk about.
But thank you very much, and I hope our watchers were as fascinated as I was as we did our science segment #1.
My pleasure.
Thanks a lot.
You bet.
Well, Heidi, that was a great interview by Barbara. Now we know what neutrinos and dark matter are.
And that's all we have for the show, Nick. Thanks again for joining us. We hope you enjoyed it, and we'll see you next week.
We'll see you next week
on Impact.